Okay, so before we go on to some new stuff today, I want to sort of backtrack a little bit and do something, cover something that I gave a little bit of lip service to last time, but didn't really go into appropriate detail. We did talk about open sets last time, and we talked about this sort of the infinite intersection rule, or infinite union rule of open sets are elements of the topology of X. And we talked about the finite intersection rule of open sets also being an element of the topology of X. We talked about the null set being in the topology of X and the set itself being in the topology of X. And anything that we can do to create a set of open sets that obey this rule will create a topology of X. That complete collection of all those open sets are the topology of X. And the reason we do this is we're after some kind of way of identifying how different points in a set, in this case our set is X, how these different points can be related to each other, how they can be defined as near, right? The idea of nearness is something that means nothing if a set is simply a list of points. But nearness suddenly begins to mean something if you have a topology. You're talking about the different kinds of open sets that can contain points, that can distinguish points. So, but I did talk about this notion of neighborhoods and using a notion of neighborhoods to define a topology. And I want to just show that this isn't the only way of working with the subject. The other way was this notion of neighborhoods, which I'll call n-hoods, because I can't spell it. The principle is very simple. We decide our set is X, the overall set we're studying is X, and P is a point in X, one element of X. We're going to say that if there's a subset of X, some subset we'll call, say, S for now, if there's a certain subset of X and we want to say that that subset is a neighborhood of P, then one thing for sure is that P is an element of S. So P is definitely an element of the neighborhood. The other thing we want to say is that if S is a neighborhood of P, and if S is a subset of N, where N is yet another subset of X, right? So N is also a subset of X, then N is also a neighborhood of P. So certainly P will be an element of N, but also just because it's an element of N doesn't necessarily mean it's a neighborhood. But if N contains a neighborhood of P, then N is also a neighborhood of P. So neighborhoodness sort of flows upwards through the subset chain. Likewise, if N is a subset of W, then W is also a neighborhood of S. So that's two things you need for a neighborhood. P has to be part of it, and it has to sort of pass up through the subset hierarchy. Then the other thing is that if S is a neighborhood of P, and if R is a neighborhood of P, then S intersection R, that's also a neighborhood of P. So that's, which means that P must be an element of S intersection R. Of course, P is an element of R, P is an element of S. If they're neighborhoods, by definition, P must be in them, by this definition. But also, it must be in the intersection. That's another rule. The intersection itself is a neighborhood. So those three things are very important ways of, well, they're the key. They're how you define a neighborhood, but there's one other that's a little bit tricky. And that trickier one says, if I have a neighborhood, if S is a neighborhood of P, I'll say S is a neighborhood of P, and if it contains another neighborhood of P, right, if there's another neighborhood of P there we'll call T of P, then S also contains a neighborhood for every point of T, right? So then any element, say little r, any element of this other neighborhood of P, if that is a subset, if T is a subset of S, then S contains neighborhoods for every R. For every R, that's an element of TP, SP contains, say, WR, where WR is a neighborhood of R, right? And I'm not going to go into this too much, but it's this last rule, this last demand on the notion of neighborhood that kind of forces us to think carefully about the notion of boundaries and limit points. But we'll speak of neighborhoods again, but the point is you could build everything you could build out of this notion of open sets and topological spaces. You could also build out of this notion of neighborhoods. And in fact, there are several different ways of achieving all the goals of topology that are met using open sets. Neighborhoods is just one. There's actually a couple others that are based on some logic. There's one that's even based on this notion of computation and measurement. There's actually a bunch. But this is the one that you really need to know, because this is probably the most, well, I guess the word is axiomatic, right? It's axiomatic, and it's very stripped down. It's minimal, I guess. I guess it's minimal. That's another way of looking at it. Although, I mean, it's hard to argue that this is an axiomatic and minimal also. But by far, this is the most canonical, right? In the sense that this is what you'll see in most textbooks. So we're going to focus on this notion of open sets and move on from there. All right, so now that we have open sets down, let's talk about the obvious next thing, which are closed sets. Closed sets. And I'll just remind you that, remember, we're dealing with a topological space X, right? So we have X and we have a topology on X. And typically we're thinking of the plane. I mean, I think that's one of the best places to start. And the plane has its usual topology of open balls, right? And then we have the line, and I showed you two different topologies on the line. Not the line, but the line interval from 0 to 1. The open interval from 0 to 1. Doesn't include 0, doesn't include 1, but we showed two topologies on that structure. So a closed set, by its simple definition, is very, very straightforward. A closed set is the complement of an open set. So the total set X minus some open set U is a closed set. So the complement of a closed set is open, and the complement of an open set is closed. And that's really the total definition of a closed set. So in our situation where we have the open ball, right, the complement of the open ball actually will be something like the boundary of the points that are on the boundary of the open ball and the entire rest of the plane, right? The entire rest of the plane. So closed sets, a single point would be a closed set as well, because the complement of a single point is the entire plane minus the point, right? And that set certainly is open. And you can tell that with the proper limiting procedure, you can produce this set, the set of all the points on the plane except this one right here, by a very cleverly arranged infinite union of open sets that just sort of circle this thing around and around and around until it just isolates one point that's not in the union. You couldn't do it for intersections, of course, because you can only do a finite number of intersections. So closed sets are easy to define because they're the complement of open sets. All right, so with this, now we can begin, and I think the next basic concept, it's hard to know what order to do this in. I mean, there is a best order, but I think the next thing we'll do is limit points, the notion of limit points. And to begin the notion of limit points, ironically, we have to now retreat back to the notion of the neighborhood. And we're still using our topological definition of a topology, right? Still we have X and the topological space. X is a topological space because it's a set with a topology, and it's exactly the way we've defined it. But even though we're defining it this way, you still can create the notion of a neighborhood with this topology. And especially what we want to do is we want to define something called an open neighborhood. And an open neighborhood is simply an open set that contains a point. So an open neighborhood of a point P is an open set that contains the point P. That's what we call an open neighborhood of a point P. Now, one of the things you can prove about open sets in general is that open sets are neighborhoods of all of its points, right? Every point inside an open set, every point contained in an open set, that open set is a neighborhood of all those points. There's not like special points. So if you have this open set, it's not like there's only special points that it's a neighborhood of. It's a neighborhood of every point inside it. It almost seems like the definition is sort of trivial, but that is important. You can define a general open set as any set that contains the point, but also contains an open set that contains the point. So then you could define this as a neighborhood, and then you would call this an open neighborhood. So you have neighborhoods, and then you have open neighborhoods. It's usually easier just to talk about open neighborhoods and skip the neighborhood thing. But one thing that is important is that any open set is a neighborhood of every one of its points. So what is a limit point? Well, in order to have a limit point, you have to be talking about another subset of points. So another subset of x. And the point P is called a limit point of the subset S if every neighborhood of P, every open neighborhood of P, also contains a point of S, right? So if this is the point P and this is an open neighborhood of P, which I'm not drawing, I guess I should stick to my, since I started doing it, I should stick to these dotted lines around open neighborhoods. Since if this is the point P and this is an open neighborhood of P, the set S, here might be a subset S. Well, there's an intersection between S and the open neighborhood of P, which I'll call that R of P, right? Or better yet, I think it's actually a bit common in the literature to call open sets U, so I'll call it U of P. So there definitely is an intersection between this particular neighborhood U of P and S, but the problem is you can see that that's not true for every neighborhood of P, because I can make a smaller neighborhood of P that doesn't have an intersection, where now all of a sudden U of P intersection S is the null set. So if that's the case, if it's the case that there exists a neighborhood of P that does not contain any point of S, well then P is not a limit point of S. On the other hand, if the point of interest was inside S, let's call that point Q, well in this case, no matter what open neighborhood, big or small, I make for Q, it will always contain some points of S. Therefore, Q is a limit point of S, right? Q is a limit point of S because every neighborhood of Q, every open neighborhood of Q, contains at least one point of S. Notice now, what's interesting about this is if you start thinking about it in terms of boundaries, right? If here is some open set, call that open set S. So, say you had a point that was on this boundary, right? And now I draw a neighborhood of that point. Every open neighborhood of that point will contain some points of S, and because of that, every point on this boundary is in fact a limit point of S. And this shows us that limit points, these limit points here, do not have to be in S. There's no point on this little line here, this boundary, which we'll just define the boundary even more intensely later, but there are limit points of S that are not contained in the set. And you can see that because every open neighborhood of this point here, this point Q, this point in question, always will have some intersection with S, and therefore it's a limit point. Likewise, if you were inside S, right, and say there was a point that was omitted, you know, S contains everything but this one little point right here, right? Well, every neighborhood of that point still intersects some amount of, let me draw it a little better, a little circle like that. That circle represents a missing point of the set S. But every neighborhood of that missing point intersects S. So even though that point, which has just been plucked out of the interior of S, that point is still a limit point of S. Likewise, any point that's in the interior of S is a limit point, right? Any point that's inside S is a limit point, and we'll have to define the interior in a moment, right? I just want to show that in this case, here's an example using our balls where every neighborhood of a point that's a member of S is also also got an element of S in it. It's almost self-evident in that circumstance. So those are the limit points. Now there's other ways that limit points are introduced. Sometimes they're introduced through the notion of sequences, where you take, you're dealing with a sequence of points. S, by the way, well, yeah, I guess that's the way to look at it. Let's look at it this way. Say the set S, I've been drawing the set S as like a region in the plane. But the set S can be just a selection of points like this, right? And the question is does this is still a set, it's a collection of points, right? And the question is, well, are there any limit points of this type of set? But the same rule applies, right? If I go to, say, this point here, well, I can find an open neighborhood that does contain a point of S, but I can find an open neighborhood of this point that doesn't. So that point is definitely not a limit point of X. The question, of course, is out here, right? When I zero in on this, what am I seeing? And if I blow that up, maybe if I blow that up, what I see is, I see this set S is getting ever and ever closer to some point P. And the way I know that P is in fact the limit point is every single neighborhood of P, right, contains a member of the set S. So no matter how small a neighborhood, and notice this is how you help get the idea of smallness. It's based on subsets now. But every neighborhood, to keep it totally general, I say every neighborhood of P has a member of S in it. And in fact, if I do this formally in terms of sequences, I have to talk about things called subsequences. And if I can say that if any sequence has a subsequence such that an infinite number of members of the subsequence is inside any neighborhood of a point, then that point is a limit point of the subsequence. It is also called a cluster point of the overall sequence. And the reason for that is if you have a sequence, it implies some kind of ordering. But you can imagine, the first point is here, the second point is there, the third is there, the fourth is there. But it could be that only every 10th point clusters and all the rest of the points spread out. But then a cluster develops, and you have to kind of pull out the sequence of clustering elements. And so you call that a limit point of a subsequence. You pull out the subsequence that clusters at your point. But regardless, the definition is the same. You have to have always, every neighborhood of a certain point always has an element of the set, whether the set is a region in a plane or a sequence of points in a plane or anything else, then that point is a limit point. All right, so once we've defined limit points, let me erase everything here, then we can talk about the closure of a set. I guess that's the next obvious thing. The closure of a set, or a subset of the topological space, X, Tx, you have your topological space. Say you have a set X. The closure of the set is the set union all of its limit points. Right? So if you had, say, an open ball in the plane, the closure would be the closed ball, because the only limit, the closure would be every point in the interior are limit points, so every one of those points is a limit point. And then everything that is not in the set but is a limit point, which pretty soon we're going to call the boundary, that's also in the closure of S. If the region S looked like this and it had just a bunch of empty points, say say S was a region of the plane that included its boundary but was missing a few points in the interior. Well, the closure would fill in those points because they're all limit points. However, if the set had like this region missing, well, the closure wouldn't fill in the region because these points are not limit points of the set S. These points are limit points here, as long as they're included in the set, and as long as the boundary is included in the set here, those are limit points, but they're already in the set. If I draw it this way, didn't include that and didn't include that, then the closure would suddenly fill them in, because it fills in all the limit points. So the closure of a set is the set plus its limit points. So now once we have this idea down, now I can zero in a little more on what I call the interior of a set, right? The interior of a set has a formal meaning, but a point P is in the interior of a set if here's a set S, here's a point P. A point P is in the interior of a set S is if I can find an open set containing P that is a subset of S. So if I call that UP, if I can find a UP that's a subset of S, then P is an element of the interior of S. And sometimes the interior of S is given by this little symbol here with this little zero checked off up there. There's a few different notations. I'm trying not to do a lot of set theoretic notation, but that would be called the interior of a set S. So P is an element of the interior if there's an open set containing P that is a subset of S. And notice for the plane topology, the usual topology of the plane, if I have a set P and a point on the boundary, which is again something we'll have to talk about in a moment, but notice that there are points out there close to the edge, in some notion of close to the edge, where there's no open set containing that point which lies entirely inside of S, right? I can't build an open set or an open neighborhood around that point that lies entirely inside of S, and therefore that point is not in the interior of S. Now, it doesn't matter whether the boundary is part of the set or not. It can lie on the boundary. It can be a member of this point can be a member of S if S includes its boundary. It's just not a member of the interior of S. That's the only difference, right? Now, the interior of a set, by the way, you can prove a couple interesting things about it. First of all, the interior of a set is always open. So given any set S, S0 is always open. And probably the most important points about the interior of a set, not only is that every interior is open, but the interior of every set is the sum of all the open sets that, so here's a set S, that's the interior of S, is also the sum of all the open sets inside of S, right? The union of every open set contained in a set S is the interior of S. And also, let's see, what was that other rule? The other rule is that, S is an element of the topology of X, which is another way of saying S is open if and only if S equals its own interior, right? And that's really important because that starts giving us intuitive ways of understanding this whole issue of whether or not a boundary is can be part of an open set. By the way, I should say that you can define a topology in terms of closed sets, something I should have mentioned. You can define this topology instead of terms of open sets, you can do it in terms of their complements, closed sets. The only difference is that the infinite union rule becomes the finite union rule, and the finite intersection rule becomes the infinite intersection rule. Just an interesting point. Okay, so that's the interior of a set. Now, obviously, the next thing is the exterior. The exterior. Oh, there's one other quick thing I should say about the interior. The interior is the complement of the closure of the complement of X. Well, of not X, but of S. So here's S, right? The complement of S is this, as we did before, where S is just one of these balls, say, that's S. This is S complement, which I think is often done by a bar. So this is S, this is the complement of S. The closure of the complement of X, well, there's nothing, the way we've drawn it here, the complement of X already contains all its limit points, so there's no change making it the closure. But then the complement of this thing is now going to be this again. So it brings you sort of back to that. So in that case, if you have an open set, well, an open set is equal to its interior. Well, the interior is the complement of the closure of the complement. So here you see you get the interior back again through this process. But if you took a set that was not, maybe you took a more tricky set, right? Take a set that actually includes its boundary and is missing a couple points. Well, the complement of that is now the set that looks like this, right? The complement is the set that looks like this and has those points in it, right? So that's the complement. The closure of that is going to be absorb the boundary, right? The closure of that is going to absorb the boundary. And then the complement of that, of what's left over, is going to be this missing those points, right? And of course, these points which aren't part of the set are not part of the interior of the set either, right? So those points come back as missing. So that's exactly what we're expecting. The interior of this thing is all the stuff in here, not including these. So that we get that through the complement of the closure of the complement. So therefore, the exterior of a set is the complement of its closure. So a set, an open set S, the closure is the set S with its boundary, and then the complement is going to be this thing. Now notice what's missing. Well, what's missing is these points that are going to be on the boundary, right? So the boundary is not part of the exterior of the set, S in this case. And the reason is the boundary is just too close to be considered exterior. You've got to be beyond the boundary. And that's captured by this definition of the complement of the closure of the set. Now, this gives us a great way of identifying the boundary, right? Because the boundary is going to be what's not in the exterior and not in the interior, right? The boundary is neither in the exterior nor the interior. So that's how we identify and define the boundary. It's neither in the exterior nor the interior. So another way of thinking about it is, say, the boundary of a set is all of the points that are in the closure but not in the interior, right? So that would just be these points out here, of course, right? Because you got to pull out the interior, but it's in the closure. Likewise, if the set is closed to begin with, well, it's just that set missing the interior. So that is how you define the exterior and the interior. Another way, there's other ways of doing it. There's other ways where they say, oh, a point is on the boundary if you can approach the point from outside the set and from inside the set. And, you know, it's a limit point of a sequence that comes from the outside and a limit point of the sequence that comes from the inside. And then, of course, you're dealing with neighborhoods that contain infinite numbers of members of the sequence, and that's also doable. But just keeping it straightforward and simple, it's the closure minus the interior. I guess that would be written like this. S closure minus S interior equals S boundary. I don't think the B is canonical notation, but these two are. Okay, so what next? We've got exterior, interior, boundary. How about density? Let's talk about density. Okay, so density, let's see. Again, we're going to talk about a subset. S is a subset of our topological space X, and we know it's a topological space because it has some topology associated with it here. So we say that S is dense in X. And this is actually strange because this is going back towards more of a property of the entire space. Well, it's a property of the subset, of course, but it's based a lot on the nature of the whole space. S is dense in X if every point in S, so P is an element of S, is either, I should put it this way. Not every point in S, every point in X. If every point in X is either also an element of S itself or is a limit point of S. P is an element of the closure. See how I can do that now? If I want P to be either an element of S, I can write P as an element of S. But if I also want to say P is either an element of S or a limit point of S, well, then I just say, well, P is in the closure of S, right? And because the closure of S contains all its limit points. So if P is either an element of the set or its element of the closure set. But remember, P itself, all that has to happen is P has to be an element of X. So I'm saying any point in the topological space. So for example, if we're dealing with the plane, I pick any point in the plane. And this point has got to be, in order for S to be dense, this random point I pick has got to either be inside S or has got to be a limit point of S. So clearly there's no way I'm going to draw S like this in this circumstance. This cannot possibly be dense in X because here's a point that is neither a limit point nor inside S. So that circumstance is totally out for the usual topology, right? For the usual topology. For the usual topology, this is clearly not in the interior or not an element of S, and it's clearly not a limit point of S based on the usual topology. If it was, then every neighborhood of this point would contain an element of that point of S, but it doesn't. Clearly it doesn't in this circumstance. However, interestingly, so before I show a counterexample to that, or before I show you how that might be wrong under a different topology, consider a different set. Let's find a set that actually is dense. And the classic set is the set of all the points that are identified by rational numbers. We played this rational number trick before in the first lecture, right? If I go to all the rational numbers, I know that I can create a rational number that is arbitrarily close to every single point in the set. Therefore, I know that if I take any P in X, no matter what its coordinates are, any point, and I draw any neighborhood around that point, I can always find a rational number somewhere that gets inside that neighborhood, right? And once I do that, that means that that point I picked is a limit point of the set. So the set of all points that are that have rational coordinates, Q, I'll call it, right? Well, that is dense in R2. How about that? With the usual topology, So there's an example of a set that's dense in R2. It's actually a much trickier concept because, like I said, we're starting to get very, this is, here's your open set, and here's an open set, and here's a subset of the plane. But there's also these other subsets that are weirder, right? The set of points with all rational coordinates. But that's what it takes to be dense, right? If you don't have this kind of behavior, you can't be dense in the topological space. These, but things get a lot worse if I switch to the discrete topology, right? If I go to the discrete topology, then every single point is its own open set. And once you do that, there are no limit points, right? Because no matter what happens to a sequence, the point that it would be limiting to is contained in its own open set. It'll never contain, if this is the sequence is the set S, and that's the point P, there's no neighborhood of P. There is a neighborhood of P that is totally disjoint with X, with S, right? Namely, the point P itself, which is now an open set because of the discrete topology. This shows you how the topology can change everything. So if we go to the discrete topology, suddenly this point P is no longer a limit point. In the usual topology, I always have to have a member of this intersection will exist if P is a limit point. So in the discrete topology, this set of rational points is no longer dense in the discrete topology because they're not limit points. You can't develop a notion of limit points in the rational numbers to any arbitrary point because there are no limit points. Nothing is a limit point of anything in the discrete topology. And that gives you a hint about how the notion of nearness is developed through the notion of topology. So that's how a set is dense. Okay, I think I better stop it there. So this has been some elementary definitions. We've covered several. We've reviewed the notion of open sets. Then we talked about closed sets. Then I think we talked about limit points, where limit points, the limit points of a set are sets who have open neighborhoods that always contain elements of some other set. Then we talked about the closure. Then we talked about, I think after we talked about the closure, we talked about the interior, the exterior, the boundary. Then I think we talked about density, right? So this gives us enough to sort of talk about the rest of what we need from topology a little bit later. Now, many of these things have fascinating little facts to it, right? There's a lot of interesting facts about the interior of sets, for example, that they're all open sets. And then there's a corresponding facts regarding exteriors of sets that are related to closed sets. The boundary, there's an interesting fact about density and the boundary, and then there's sets that are nowhere dense. And there's all these interesting theorems that depend on these concepts. And all of these concepts that we've talked about have all been based on the topology. We even saw an example how changing the topology changes the whole notion of say, density, I think was the example we used. But changing the topology changes the nature of limit points. It changes a lot of things. And that gives us a sense that the topology is a way of understanding the notion of nearness. And we'll get a much better sense of that in a next lecture, because in the next lecture we're going to talk about separability. And separability is essentially the core nature of the notion of nearness. And we're going to see how that is entirely dependent on the topology we choose. Okay, we'll see you next time.